Hey guys, here we are in part 2 on our lesson about thermochemistry. Today we're going to be talking about measuring enthalpy changes. Enthalpy is just a fancy word for heat. Alright, so whenever we see that word, just refer to it as heat. So we'll do a few things here. I'll talk about what a calorimeter is. It's very important in discussing heat changes. We'll do some calculations involving enthalpy changes. We'll take a look at what thermochemical equations are, and then finally how to develop a heating and cooling curve. What I want to point out first is what a calorimeter is. This is used to measure the heat of chemical reactions. So basically all you do is you take something you want to measure how many, say, calories it is. So let's say we want to figure out how many calories are in a cheese doodle. So we'll take a cheese doodle, let's put it down here inside this little crucible, which is just a ceramic container. Notice it has a heating coil going into it and some heaters. It has some oxygen pumped into this steel bomb. This thing here is called a bomb. These are typically bomb calorimeters. All right, so we're going to ignite the cheese doodle. We're going to heat it up. And what's going to happen is whatever heat it generates, it's going to move through, heat up the bomb, and then start raising the water temperature inside this bucket. This is how we end up measuring calories, by the heat change that occurs when a reaction is happening. This would be a combustion reaction. We simply measure how much the water temperature goes up and we can calculate the calories. That's basically the calculations we'll be doing for this unit. Heating up a cheese doodle is an exothermic reaction because it's giving off heat, but you could also do this for something that's an endothermic reaction. Say you put vinegar and baking soda inside here. What's going to happen is it's going to start cooling down. The temperature is going to go lower. So you could do it for either exo or endothermic reactions. Okay, so here's our main formula for calculating the heat of a reaction. Notice what's going on here. Q stands for heat. M is the mass, typically in grams. Specific heat we can either solve for or use a chart. I have included here the thermochemistry part in your formula sheet, so this is really important stuff that you should have handy. So here's some values of specific heats, and unless you're solving for it. Temperature change. So the way we do temperature change, it's always the final minus initial temperature. That's how temperature changes go, because it depends on if this is a negative or positive number, it's going to affect whether Q is negative and positive. That's going to determine if your reaction is exothermic or endothermic. If it's negative, it's going to be exothermic, because exothermic is when heat is exiting the system. If heat is leaving the system, you have less heat, so that's why it becomes negative. Endothermic is when you're absorbing heat, so you're adding more heat into the system, so Q becomes positive. Let's go back to this problem here. So here's our formula. Q equals mCp delta T. All we're doing here is plugging in some numbers. M is our mass, so we have a 25-gram sample of titanium. That's M. Our specific heat is given to us. Specific heat of titanium, there it is, 0.5526. And our temperature goes from 75 is our final, so put that first, 75.25 minus 25.25. Okay, that's going to give us 50, so it's 25 times 0.5526 times 50. We do this math, and we get, I'm going to round it to 691 joules. This is a positive number. Our Q is in joules. It's in joules because our specific heat was given to us in joules. See the J there? Typically, we're using joules in most of our calculations. Okay, so this is a positive Q, so this would be an endothermic reaction. This system is absorbing the heat to do this. Let's take a look at another one. An unknown substance with a mass of 100 grams absorbs 1,000 joules while undergoing a temperature increase of 15. What is the specific heat? This time we're solving for specific heat. Same formula. Okay, let's plug in the numbers that we have. We have 100 grams. We're solving for specific heat, so that's like our X. And then our change in temperature, it says it increases by 15 degrees. So we don't have to do any calculations. We just put the 15 in. If it says it's increasing by 15, this is going to be a positive number because the final is going to be more than the initial. It says we have 1,000 joules of energy, so that's our Q. Okay, 1,000 joules is our Q. That's our energy. So here we go. All we have to do is solve for X. So 1,000 equals 100 times 15 X. Do some algebra. And there we go. This is our specific heat. This is always going to be a positive number. So just keep that in mind. Let's try another example here. Same formula, Q equals MCP triangle T. Let's see what we have. Graphite has a specific heat of 0.709, so that's our CP, 0.709, 25 grams. The graphite is cooled from 35 to 18. So our final is 18 minus 35. This is negative 17. So 25 times 0.709 times negative 17. This comes out to negative 301. Joules. All right, so this time, because our Q is a negative number, this is exothermic. Exo. This system is releasing heat. And think about it, as something is cooling down, how it's giving off heat to become cooler. Okay, so let's go on to what a thermochemical equation is. Sometimes we calculate energy by using specific data given to us. So here's a thermochemical equation. Looks like a regular equation, right? Except look, it has this information here as part of the reactants. If the amount of energy is a reactant, that means it's absorbing heat. And absorbing is endothermic. Okay, if it said had the plus on the other side here with a number of kcals or joules or whatever, then that would be exothermic. All right, so let's see what's going on here. Calculate the energy required to produce 4 moles of Cl2O7. So our equation here tells us 130 kcals makes 2 moles of Cl2O7. If you had 4 moles, what do you suppose? This is going to be, you're going to go twice as much from here, so your answer is going to be twice as much. You would need 260 kcals for 4 moles. That's really all you have to do. There's really not much of a calculation there. You just have to realize what's going on. It's kind of obvious. You're only doubling it here. So one way to do this is if you have 2 moles required 130 kcals, how many would 4 moles require? You could do it this way too when it's not so obvious that you're just doubling it. This is going to be an equal sign because this is just a ratio. So we could do this math here just to see how it works out. This is going to be crisscross math. All right, so you're going to kind of do this. So 2x equals 130 times 4. So 2x is going to be 520. 520, and we're solving for x, so divide by 2. 520 divided by 2 is 260. And that's what we got up here. All right, so you can just do these problems as a ratio, just set them up this way. They're usually pretty easy. What may happen here is you may have a question that asks you about grams. So what you have to do is use our favorite formula to solve that problem. Thermochemical equations, not too difficult. So let's talk about doing a heating curve. This is used to calculate how much energy is involved to take an ice cube. Say we have a 25-gram piece of ice at negative 20 C, so this is an ice cube minus 20 C. How much energy is going to take to convert it to steam at 150 degrees? Draw a chart like this where we have our temperature, and then here we have energy. So the first thing I'm going to want to do is I'm going to look at our question and see what temperatures we're talking about here. So we're starting at negative 20 degrees Celsius, so that's where we're going to start. We're going to have our ice cube at negative 20. We're going to put in 0 degrees and 100 degrees because this is the melting and boiling point of water. And then finally we'll go up to 150 degrees. This is degrees Celsius. This is increasing energy. So here we have an ice cube at negative 20 degrees C. As we add energy to it, it's going to eventually get up to 0 degrees. So first, we have to understand what state of matter this is at this point. What state of matter is liquid between 0 and negative 20? This is ice. Okay, so let's just keep going. Let's see what happens here. At 0 degrees, we have ice. And what happens as the ice is melting? As the ice melts, as we add more energy, the temperature does not change. It stays at 0 degrees the whole entire time until it's nothing but water. This is my little symbol for water. So it's important to understand that the temperature does not change as ice is melting. So when you're at the beach and you have a cooler of your favorite beverages and a bunch of ice, as the ice is melting, that water temperature stays at 0 degrees the whole entire time until all the ice is gone. So don't dump your water out. That's good, cold water right there. This has a special name for it. This is called the heat of fusion. This is when we have a phase change. This is called a phase change, where we're going from a solid to a liquid. There is no temperature change during a phase change. Okay, so let's keep heating up our water here. So we're at 0 degrees water. We're going to keep heating it up. We're going to get to 100 degrees Celsius. What state of matter is water between 0 and 100? This is when it's a liquid. Okay, so what happens at 100 degrees? At 100 degrees, we still have our liquid, right? Imagine you're going to boil some water. We have a 100-degree liquid. We keep adding energy to it. It stays at 100 degrees. This is another phase change. This is called the heat of vaporization. Same thing happens. As you're boiling your water, it's slowly evaporating until you get to a gas phase. This is my hieroglyphics for a gas. So we're going from a liquid to a gas. This is called the heat of vaporization. It's another phase change. okay? And the temperature does not change. As you are boiling some water to make some pasta, your water is at 100 degrees. It's boiling away. It's turning into steam. That water is still 100 degrees. It's until there's no more water left. So even if you turn up the oven, your stove, if you turn up the heat on your stove, the water temperature is not going to go above 100 degrees. Once all the water is gone, you keep heating all that steam. You can keep heating it up. What state of matter is water above 100 degrees? It is a gas at this place. All right, so we have 5 distinct things going on here. We have ice, we have the heat of fusion, we have our liquid state, we have the heat of vaporization, phase change, and then we have it turning into a gas. So this is the journey of an ice cube from -20 up to 150 degrees. We can calculate how much energy this entire process takes. The trick here is we have to do it in 5 different steps. We can't just use this equation to determine this entire process. We're going to have to break it down. Here's how we're going to do this. We're going to need this information. This is from your formula sheet. We're going to need some specific heats here. Notice water, this really should be liquid, ice, and steam. We have our heat change formula, which we've been doing, but this is new here. This is the heat change at a phase change. Notice this doesn't have a change in temperature because at a phase change there was no change in temperature. Remember? At 0 degrees, it stays at 0. At 100 degrees, it stays at 100 until it moves past it. So that's why we're going to use this formula. This delta H, this stands for the change of enthalpy, which is heat. So all we're going to do is we're going to use these numbers here. Delta H of fusion is 335. Delta H of vaporization is 2260. So let's see how we do this. So step 1 was when we had some ice. So first of all, we're going to use this formula because there was a change of temperature at this point. So our mass, M is mass, it was 25 grams. We're talking about ice here. Let me write ice here so we remember. The specific heat of ice, we come to the table here, we're going to use 2.10. And our change of temperature, it went from -20 to 0. So that change is 20 degrees. So we'll plug in 20. Okay, we do the math here. We're going to come up with 1050. All right, this is in joules. All these values are going to be in joules because our specific heat is in joules. Okay, let's go to the next step. The next step, number 2, is the heat of fusion. This is where we have a phase change. So we're going to use, I'll put fusion here, step 2. This time we're going to use the phase change formula, Q equals M delta H. So we have our mass still 25. It's going to be 25 for all of these. That mass doesn't change. It's right here. The delta H of fusion right here. Plug in 335. Multiply 25 times 335, 8375. Okay, so this is how much heat is for an ice cube melting from -20 to 0. This is the amount of heat of an ice cube melting from a solid to a liquid. This is the phase change. Step 3, we're now up to the liquid portion right in here. So because we do have a temperature change, we're going to go back to the main formula, Q equals mCp delta T. Our mass is still 25. The specific heat of our liquid right here, 4.18. This is why we have to do it in all these different steps. And our change in temperature, it went from 0 to 100. 0 to 100. So that's our change in temperature. Put 100 in here. Multiply those three numbers. I get 10,450. So that's a lot of energy for changing some water from 0 to 100 degrees. Step 4. Here we are here at our phase change going from a liquid to a gas. This is the heat of vaporization. Because this is a phase change. This is vape. Step 4, we're going to go back to the phase change formula. But this time we're going to use, still 25 for the mass, this time we're going to use the heat of vaporization number, 2260. Okay, no temperature change. Multiply those two numbers, 56,500. Look how high that number is. This is water turning into steam. This is why steam burns and is very painful if you've ever burnt yourself on some steam. It's got a lot of energy going on there. And finally, step 5 is our gas phase, where we go from 100 to 150. So I'll put gas here. Step 5. We're going back to Q mCp delta T. Again, the mass is 25. Our specific heat for steam, here we go, it's 1.7. And then the temperature change went from 100 to 150. So that temperature change is 50. People make a mistake of going from 0 to 150 or negative 20 to 150 or whatever, but no, it's just the gas portion that we're interested in, 100 to 150. So that temperature change is 50. Multiply those three numbers and I get 2125. So this is the amount of energy for each of the different phases, but because we're interested in the entire amount of energy, we're going to add all these numbers up. This comes out to 78,500. This is in joules because, again, we're using joules as our specific heat. The question says kilojoules. So to go from joules to kilojoules, we just have to divide by 1,000 because 1 kilojoule equals 1,000 joules. So what you would do is a little dimensional analysis here. This is joules on top, joules on bottom. 1,000 joules is 1 kilojoule. So you end up dividing by 1,000 and you get 78.5 kilojoules. So that's how much energy it takes to take an ice cube from -20 and convert it to steam at 150. When you do these problems on your own, you don't have to draw the chart if you don't want to. You can if it's helpful. Otherwise, you can just look at the question and get all your information. But these problems will always consist of these 5 steps. We can do the same thing for a cooling curve. It's just the opposite. The numbers are the same process, you just do it backwards.